Hi everyone, today we're going to talk about isomers. Isomers are compounds that have the same molecular formula but different chemical structures. This is a chart that shows the different types of isomers. The two major types are constitutional isomers, which differ in either the functional group or the position of the functional group, and stereoisomers, which differ in the 3D arrangement of the molecule. So first, structural or constitutional isomers. These differ in the covalent arrangement of their atoms. This means either the position of the functional groups is different, or there's a different functional group. So for example, I have three isomers of the same molecule. First, can you tell me what the formula, the molecular formula, is for all three of these molecules? What is the difference between number 1 and number 2? Is it a difference in position of functional group, or do they have different functional groups? It helps sometimes to name the molecules. What is the name for number 1? What is the name for number 2? So the name for number 1 is propanol. It has an alcohol group coming off carbon number 1, or a hydroxyl group coming off carbon number 1, and it has 3 carbons, so it's called propanol. Number 2 has also an alcohol or hydroxyl group with 3 carbons, and so it's known as 2-propanol, or it's also known as isopropyl alcohol, or isopropanol. What's the difference between the isomers in 2 and 3? Is it a difference in position, or do they have different functional groups? Number 2 and number 3 have different functional groups. Number 2 has an alcohol or hydroxyl group. Number 3, this is a functional group we haven't talked about yet, but it's called an ether. So again, the names, the first one is propanol, the second one is 2-propanol, or isopropyl alcohol. And the third one is named by listing the side chains coming off the ether, and so it's methyl ethyl ether. The next group are stereoisomers. They differ in their three-dimensional orientation, and there are two types: cis-trans isomers and enantiomers. Cis-trans isomers differ in their arrangement around a double bond or a ring. Cis refers to the functional groups on the same side, and trans refers to the functional groups are on different sides. So in this case, we have the same molecule, it has the same molecular formula. It has a double bond in the same position off of the second carbon, but the two side chains coming off that double bond, like these two methyl groups basically, these are on the same side, so it's cis, and these are on opposite sides. This also happens with molecules with rings. So in a double bond and a ring, the reason why you can have isomers where you don't have this in single bonds is because the ring and the double bond can't rotate around that double bond or that ring. And so if you have an arrangement where they're on the same side or different sides, they're going to stay that way. If you had a single bond, they're actually going to rotate to the position where they're most stable at. In this case, again, we have 2-bromine coming off of the same side of a molecule, so this is a cis. And on this one, we have 2 that are coming on opposite sides, so it's a trans. So there are, for instance, a couple isomers of different monosaccharides. This is an example of a D-glucose, and I'll explain what the D means in a minute. And in water, it can form either alpha glucose or beta glucose. Is beta glucose a cis or a trans isomer? The interesting thing about beta glucose too is when it forms polymers, the polymers of beta glucose or cellulose are not digestible by mammals. We don't have the enzymes to break the linkages, whereas we do have the ability to break linkages between alpha glucose in polymers such as starch and glycogen. In this question, which of the following of these molecules can form cis-trans isomers? In order to help you answer this question, there are two basic rules. First, rotation must be restricted in the molecule, either around a double bond or a ring. Secondly, there must be 2 non-identical groups on each of the doubly bonded carbon atoms, or on each sides of a bond in a ring. Okay, in this case, take a look at A, for instance. You'll see this is the doubly bonded 2 carbons. This one has a Cl and an H. This one has an H and a Br. So first of all, rotation is restricted by the double bond. Secondly, each of these atoms has 2 different atoms coming off it. This is a Cl and an H coming off this carbon. and this carbon has an H and a Br. You take a look at this next one. Again, we have restriction because of this double bond. If we look at each of the carbons, we have to look at what the side chains are. In this case, it has 2 hydrogens, so that fails the second rule. I'm going to let you take a look at C and D on your own. Enantiomers are mirror images of each other. In this case above, these are both the same molecule, so they're isomers. They have all the same functional groups. They all have them off the same carbon, so they're not structural isomers. And there's no double bonds or rings, so they're not cis-trans isomers. The difference is actually that based on how they are ordered around that central carbon, they can actually have different functions. If you actually try to put these and try to superimpose them on top of each other, because of that different order, they're not the same molecule three-dimensionally. Enantiomers in the past have actually caused some problems with different medicines. There have been medicines in the past that have accidentally included enantiomers that were not helpful for certain symptoms, in fact were toxic. In biology, we use a D or an L to represent if they are right-handed enantiomers or left-handed enantiomers. In other fields like chemistry, they use R and S, which actually lists them based on their molar mass of the functional groups around the central carbon. But in biology, the D and L actually come down to glyceraldehyde. And if we're going to label a molecule as D or L, it's based on which glyceraldehyde, a D or L, would have to be actually molecularly changed or go through actually reactions to form the molecule that we're talking about. Now, we're not going to discuss how you do that and how you label them D or L glyceraldehyde. What we're going to focus more on is actually just being able to recognize them as enantiomers. And you should also know the following too. Amino acids that are in living organisms on Earth are the L form. Why I say on Earth is because it's interesting, there have been meteors that we've found other amino acids of the D form too that have been formed in outer space, not formed from living things on Earth. Monosaccharides are usually the D form. For example, the major monosaccharide of glucose is the D-glucose version. In fact, if you were going to look for any glucose in any chemistry supply room or biology supply room, you wouldn't look for glucose, you would look for dextrose, the name for D-glucose. And the difference is here, guys. Again, this is the OH, or the hydroxyl group, the alcohol group. And if you look, they're in the same positions as a D and L glyceraldehyde. So now I have 5 molecules here. And these 5 molecules are all isomers. So first, I want you to find the molecular formula of all of these isomers. Which 2 of these are enantiomers? Which 2 of these are structural isomers? So really quickly, I wanted to go through the names. A is actually D-glucose, B is D-mannose, C is D-fructose, D is D-galactose, and E is L-fructose. In this question, these are also all carbohydrates, but they're shown in a ring structure. Usually in water or aqueous solutions, glucose and other carbohydrates form these ring structures. These are not all isomers. Which one of these is not an isomer of the others? Okay, whenever we also name glucose molecules and we're looking at the structure of glucose or any other carbohydrates, we number the carbons just like we do in other organic molecules. And we start actually from the oxygen right here. And we number around from 1, 2, 3, 4, 5 to the branch one off, 6. In which 2 is there a cis-trans isomer of carbon 3 and 4? Okay, that's all I have for today on isomers. I hope you're all staying happy and healthy. Bye.